Hello, I'm Daniel. I wanted to take about 10 minutes to talk to you about the very important chemical property of electronegativity. The idea that each element has a tendency to be negatively or positively charged is an old one. The legendary Swede John Jacob Berzelius categorized elements in just this way long before we knew anything about the structure of atoms. Today, electronegativity is defined as a measure of the strength to which atoms of one element are able to attract electrons or electron density from atoms of another element. Knowing the relative electronegativities of different elements enables us as chemists to make all sorts of reliable predictions about the nature of bonding in molecules and compounds. In particular, it enables us to understand the extent of covalent and ionic character in any bond. While the concept of electronegativity seems clear, and as experimental chemists we could use our chemical intuition to produce some sort of rank ordering, it is not at all obvious how we could quantify or measure this important elemental property. So when you go and look up electronegativity values, you'll always find it's qualified. Sometimes you'll find Pauling's values, sometimes Mulligan's electronegativity, sometimes it'll be the Alro-Rocco psych scale, and sometimes Allen's values. In this video, we're going to look at each of these fundamentally different approaches to quantifying electronegativity, and then, when you know how they are derived, you can see why they all produce such similar results.
Let's start with the original quantification by Linus Pauling in 1932. The American chemist Gilbert Lewis had been formulating his valence bond theory, chemical bonding. Here we imagine that a heteronuclear bond can be thought of as a combination of perfectly shared electrons, a covalent bond, and an unequal sharing from an ionic bonding interaction. Pauling saw a connection between the bond strengths and the electronegativity differences between the pair of heteroatoms. He reasoned that the heteroatom bond strength could be thought of as a covalent contribution, which, he says, is the average of the two relevant homonuclear bond strengths. And then there is an electrostatic ionic contribution, which becomes greater the greater the difference in the heteroatom electronegativities. Using known thermodynamic data from homonuclear and heteronuclear bond strengths, and fixing hydrogen at 2.20, and using some chemical intuition, i.e. saying that fluorine is more electronegative than hydrogen, he assigned electronegativities to many elements, and over time, as more data has been gathered, this list has grown. So this is the Pauling scale of electronegativity. Cesium is the lowest, and fluorine is the most electronegative. The key feature of the Pauling electronegativity scale is that in general, the value D is going down a group, and increases going from left to right across the period. So the S block are the least electronegative, or the most electropositive if you will, and the halogens, and fluorine in particular, is the most electronegative element. Time to introduce Robert S. Mulligan, not to be confused with Robert A. Mulligan of oil drop fame. It's a curious fact that the pair did know each other. Robert S. Mulligan attended the lectures of Robert A. Mulligan. Mulligan proposed a different way to quantify electronegativity. He said, if electronegativity is about the relative ability for an atom to give or take an electron, then we've already measured that for atoms in isolation. The first ionization energy measures the energy required to remove an electron from an atom. And the electron affinity, well, that measures the energy released when a neutral atom accepts an electron. The difference in these two can give us an electronegativity which scales linearly with Pauling's values. So we don't need to worry about extracting thermodynamic quantities like bond energies from complex compounds as we did for the Pauling electronegativities. Now, for the Mulligan electronegativity, we can use spectroscopic data on pure elements. That's okay, but it's not always easy to measure electron affinity. A little while later, Louis Ulrich and Eugene Rocco gave us another perspective. They said electronegativity is a measure of how strongly an atom holds on to its outermost electrons. That's okay, but calculating the exact force experienced by the valence electron is mathematically too difficult for any atom with more than one electron. However, there is a workaround. The inner electrons, the core electrons, are largely inside the orbits of the valence electrons. And these core electrons will screen some of the actual nuclear charge. We can simplify our model of atomic structure and say that the valence electrons feel a reduced effective nuclear charge, ZF. So the force experienced by a valence electron will be proportional to the effective nuclear charge, but inversely proportional to the square of its average distance, or in this case, the size of the atom, radius r. We can calculate the Alreed-Rocco electronegativities, and they have a linear relationship to the Pauling values, and so can be scaled for comparison. That brings us to Leigh Allen. He said, forget about bond strength anomalies. Forget about the ionization and electron affinities. He said, don't worry about the force on the valence electron. What he said was the electronegativity was simply the average energy of the valence electron in an atom. Those with the least amount of energy are the easiest to remove, and those with the most energy are held most securely and are the hardest to remove. His formula is a sum of the energies for the electrons and p orbitals divided by the number of s and p electrons, so the average energy. No surprise here, we get values that scale linearly with Pauling's original electronegativity. Again, we can obtain values for all the elements, including the noble gases. And by this method, neon is the most electronegative element. It certainly holds on to its outermost electrons most strongly, but we must remember, with a full shell, there is nowhere to put an extra electron, which accounts for the incredibly stable and unreactive character of this element. These are the most common measures of electronegativity. They use different quantities, yet they produce the same qualitative ranking of elements. And even now, 90 years after Pauling's original publication, we still see new studies in this field. Tantadini and Oganov have just published a revised scale of electronegativity in the journal Nature. In general, it really doesn't matter which type of electronegativity that you use. They all give good enough values to make semi-quantitative predictions about structure and bonding across a wide range of compounds and materials. There is just one other aspect of this story that I'd like to highlight, and that is how the different approaches all work to give us a better understanding, allowing us to progress in the subject. In chemistry, atoms are just too complicated to be able to model exactly. Schrödinger's equation of atomic orbitals becomes mathematically intractable with more than one electron, meaning we can't calculate exact solutions for elements heavier than hydrogen. But there's the skill of a chemist. We don't always need to be exact and precise to find the answer. Constructing and parameterizing a simple model is often all we need to do to gain a deeper understanding and give us great powers in predicting the chemical behaviour of elements. If you like this, please like and subscribe to encourage me to make more videos. Thank you.